All right. Good. Good annotation chat. Here we go. Yeah, so students, remember, feel free to ask questions in the chat as we go through. So there's a lot of content that we'll be talking about today. But let's start it off with a little bit of logistics as to what's to come in the class. Can you guys all see my screen and hear me well?
Yep.
Good, 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 good. Awesome. All right. Um, okay. So logistics. So in the class over the next few weeks, we're going to be so today we're going to do a deep dive. We're going to do a deep dive lecture that covers everything that you need to know to be an expert in LLMs and like AI in general, right? So by the end of today's class, you should understand all of the relevant AI that's necessary to know what's going on under the hood. So last time we had a little bit of an introduction on this. Today, we're going to have the full deep dive. Let me see. Oh, wait, are you guys, hold on. Let me make sure you guys are seeing the right screen. Okay, so we're going to have the full deep dive. However, so I've just sent out emails to join the Piazza. So make sure you join. If you haven't gotten an email, reach out to Loggy. Loggy's going to get you in the system. He's going to make sure that I know so that we can make sure that you're in the system. Um, so do that if you haven't seen the email already. Now, so we're going to be forming groups of 2 to 5 people. And so it's going to be, I mean, Loggy is always there to help facilitate. If you need a group member, but get on the Piazza, get on the, in the Discord. So I also shared a Discord link that everyone's invited to. So get on these services. So Piazza is an email. Let me just clear all drawings and make sure that I have the vanishing pen. So Piazza is via email and Discord. There's a link here. You'll have the slide. The link is also shared through Piazza, so everyone can get access through there. So we're going to be forming groups of 2 to 5 people. These groups are essentially the main project groups. So these are going to be the groups that's relevant to the project competition. Over the next few weeks, however, we're going to have some project readiness assignments. So these project readiness assignments are essentially going to be a set of individual assignments that will give you practice and introduction to the set of open source tooling that we're going to be using in creating these projects. These projects are going to be end-to-end AI applications using LLMs, using generative AI models to build something cool and interesting that is only possible with the advent of LLMs. And so let me just move the camera so you guys can see me better. Okay, that's essentially using LLMs, and so that competition is going to have prizes, right? So first place is going to be earning 500 USD. Second place is 200 USD, and third place is 100 USD. So it's going to be fun, right? And these projects are going to go on like once we get started after the lectures and the assignments. So we're going to do that over the next 4 or so lectures, sessions. After that, we're going to go into the project competition mode where there will be weekly meetings and essentially I'll be available to me and some other folks from the team are going to be available to a number of groups to help with the projects, right? Just kind of provide like day-to-day guidance or week-to-week guidance around the projects and give you guys assistance there and the relevant concepts. So So bear this in mind. This is what's coming up in the next few weeks. Get on the Piazza, get on the Discord. I'm always available on the Discord, so you can always direct message me. And then you can direct message each other as you guys go on this journey. Logi's also always infinitely available. And so this is what's coming, right? Next week, we're going to do a deep dive on the content of this slide. So this slide is really going to be explained in depth when we talk about the individual projects. And we start talking about the major project, right? Where you're going to build something end to end and potentially fine tune a model for a specific use case. And you'll really get hands-on experience building awesome solutions and awesome products and projects with the kind of generative AI that represents, what's now going to be defining our future when it comes to this technology and technology stack, right? So, all right, so that's coming up. Any questions on that? Feel free to throw any questions in the chat, guys. Or you could ask out loud, if that makes sense. All right. All right. And don't hesitate to direct message me in the chat. Oh, can we form groups on our own interest? Absolutely. So these projects, there's going to be very, very loose requirements, right? Like if you have a project idea, or you have an interest, a set of interests, you can form groups around those interests, right? There's actually flexibility in what you build, but the parameters around it is going to be, it's got to include generative AI LLMs, and in that build out using a certain set of open source tooling, right? So you're going to have to learn and use a certain set of open source tooling. That includes many of the innovations that's coming from the incubation lab in Sri Lanka, as well as University of Michigan, as well as Jaceki Labs. We're all collaborating on this open source mission to create the future tools that can accelerate our ability to develop such things. And so we're going to use those tools and we're going to use cutting edge LLMs to build out great ideas. What they solve, the solutions they solve, that has flexibility. I'll offer some suggestions, but you guys can actually go off and build something from your heart's content, right? Like your heart's desire. So very good question. Thank you, Diva Karan, or Diva Karan. Yeah. Feel free to correct me if I got that, if I didn't do a good job with that name. All right. So, yeah, awesome. Very good. So, all right, let's jump right in, guys. So today is a very big day, and this is a very important lecture. And it may go over, and that's okay. Stay with me because it's going to be worth it. We're going to go from soup to nuts on exactly what's going on. So if you remember last time we talked about this picture, and really this is just to orient you guys. We're going to go deeper. We're going to really understand what's going on in this lecture. And you will be so empowered, right? And you'll see what I mean by the end of this lecture. So I'm starting here just to remind us what a neural network is, okay? So neural networks are neurons with synapses. These are called weights. The design of this interconnected network is called the neural network architecture. This is the architecture of the neural network. These are neurons. These will emit values based upon an input. So it'll see this set of inputs, sum them up, and it will emit a signal cascading through this feed-forward neural network, right? So I'm restating some of the terminology. I realize maybe half the class, this is the first time you're really getting to see what a neural network is. These are the terms, right? Feed-forward neural network architecture, the simplest deep neural network. It's deep because there's multiple hidden layers. So the layers in the middle of the network are called hidden layers. You'll hear this terminology, especially as you read papers. So it's important to understand what they mean. And then these are your weights in this simple feed-forward neural networks. And these weights, you can think of it as magic values so that when this input layer sees pixels, which are values between 0 and 1 being white, 0 being black. When this input layer sees pixels, these values capture the intelligence. The coefficients, numbers between 0 and 1, let's say, of each of these lines are configured such that when the signals go in for these 884 pixels, when the signals go in with a certain configuration of 884 pixels, let's say this configuration of this picture, then the output signal is going to be strongest for the right answer, right? So the weights have the intelligence. These are an assortment of values between 0 and 1, such that when the values between 0 and 1 go in for each pixel, 884 of them, the right answer comes out. And we get these magic weights via training. We train the model, we force the model to have the right values for this weights. We call that an intelligent model. The model that has the right values for those weights. Okay? So this is that. Recap. This is summary, right? So this model, very cool model, knows how to look at pixels and then tell you what the right answer is. And the architecture is such that the neural network architecture has one node per pixel, one input node on the input layer per pixel, and then it has one output node per determination of value per class. So these are this is a classification. It's classifying what is the number in this picture. Picture goes in here, class comes out here, and the classes are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a neural network. This is one of the first popular neural networks that beat humans at a task. So this neural network beats humans at recognizing digits and images. Like humans do worse. This simple, small neural network does better than humans. It's very interesting, right? So that's a neural network. Good. Now, let's jump in. Now we're going to get into some real understanding of what's going on here. Okay? So, okay, well, how does this link to a LLM? How do we go from this to LLM? Well, the first thing we have to understand is, what does the model see? Okay, this is straightforward. It's seeing pixels, values, grayscale 0 to 1, where 1 is white, 0 is black, anything in between is gray. It's seeing a grayscale pixel, 884 of them, between 0 and 1. Okay, cool. That's what this model sees. Well, how do you deal with words? Right? Because we know the the LLMs that we love, ChatGPT, GPT-4 sees words. So then, like, how do we do that? Well, neural networks are mathematical models. This is math, right? So we got to get those words to turn into numbers somehow. How do we turn a word into numbers? You can think of a million ways. And I'll give you the see through the matrix, the force is with you insight. It actually doesn't matter how you represent the numbers, the words as numbers. It actually doesn't matter. You could just enumerate all the words in the language and then just call those the numbers that go into the model. And then you could train a model with that representation. But that's an inefficient representation. Okay, I'm going to pop the stack on that sage level stuff. Let's talk about how people do this, right? Like, let's just get into the details. Okay. Okay. You got to get the words into numbers. Okay, it's very simple. You'll see this is the established way. First cut. Every single process to build awesome generative AI LLM goodness, if you were to start from scratch, you start with this. This is called a one-hot encoding, right? So I said there's many different ways that actually doesn't matter. That's true, but this is the established way that people do it. One-hot encoding. Okay, what's a one-hot encoding? This is actually an embedding of words, and it's naive. It's a naive embedding. Let's talk about how it works. So we'll just go to the examples. If you take V is vocabulary. Vocabulary means all the words that you can say in said language. So let's say English has 500,000 words, right? The English language has if you were to like put all of the diction, you took the dictionary, there's 500 words in that dictionary. Each word needs to have a number that represents it. And the way we do that is something called a one-hot encoding. That means you take a vector of the size of your vocabulary. Now, question for the audience. Does your vocabulary always have to be all the words in the English language? Think about it and drop something in the chat. I'm going to move on, but I'm going to watch the chat to see if anyone answers this question. The question is, in practice, when you train a neural network, do you always, and you're just using one-hot encodings, do you always have to use a representation that captures all the words in the English language? Or what other thing can determine how big your vocabulary is? Well, what else can determine how big a vocabulary you need? How big of a vocabulary do you need? Is it all words in the dictionary? Always. I'll leave that one for you. If anyone answers it, we'll talk more about it. Okay. Give it 20 seconds to see if anyone wants to chime in. All right, I'll come back to that. So, but feel free to drop something in the chat. All right, so here we have a vocabulary. There's 3 words in it, right? Dog bites man, man bites dog. Here are one-hot encodings for the words. You essentially, it's one-hot because you have a vector of the size of your vocabulary. In the case of the English language, by default, would be 500,000 indices in this vector, 500,000 dimensions in this vector, 500,000 indices in this list, you could think. And only one of them is going to be 1 and everything else will be 0. That's the most simple way to represent words as numbers. We can think of it as maybe a binary value with as many bits as you have words, and 1 bit is on for each word, right? So that's one-hot encoding. This is actually what the model sees. Okay. So for this vocabulary, it's pretty simple. You only have 3 elements, right? You only have 3 elements. Dog bites man, and dog will be 1. Bites will be 1. It'll be hot on the first index. Bite will be hot on the second index. Man will be hot on the third index, right? Okay. So then when you flip it all around, you just man bites dog. It's the same representation of the word. The word is an assortment of these values. This is a one-hot encoding, right? So let's look at another view of a one-hot encoding. Here we are. Our vocabulary is a little bigger. So we have 1, 2, 3, 4, 5, 6, 7, 8 words. So we have our encoding has 8 dimensions. It has 8 indices. It has 8 values. And only one of those values will be hot, or 1, for each of the words. Very, very simple way to represent words. Okay, so this is baseline. If you just had your language and you're like, okay, I don't have pixels that are easy grayscale. I need some way to represent this as numbers, because neural networks is just a mathematical formula. It can only see numbers, real values, right? How do we establish that? Well, this is a one-hot encoding way of establishing that. And let's see how this actually looks, right? So last time, if you remember, we talked about CBOW, continuous bag of words. We talked about CBOW in the context of the first revolutionary thing that gave us the concept of pre-trained AGI style, artificial general intelligence style neural network models. Well, so we looked at this kind of task, right? You've got a window of words, and then you do some activations, and then you have a word prediction out. Well, in a one-hot encoding, let's take this down to just to look at what this looks like in a one-hot encoding and how it maps to a neural network model. Let's take this window size down to 1, and then let's look at what one-hot encodings look like, right? All right, so this is window size 1, and this is what the model sees. So the input layer of this neural network, we looked at the other drawing of a neural network for the digit recognizer that only sees pixels. Now we're looking at a model for a word predictor. It'll predict the word that's in the middle. Cat blank on, cat sat on. Word in the middle predictor. This is the same feed forward mechanism as the digit predictor. The digit classifier, it looks at 5 and then it's like, that's a 5. This is the same neural network architecture, except the input layer, it's not looking at pixels of grayscale between 0 and 1. It's looking at many nodes. Let's say you had 8 of these nodes. It's looking at 16 nodes, and it's organized such that it'll see zeros on most of the nodes and 1 in just a few places. That's the input layer, right? And then it goes through the hidden nodes, and then it outputs a smaller set of values. Remember, we were looking at 768 pixels, and then we had 10 outputs, like just 10 values, because we're picking between 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Here, we just need, let's say 8, similar to the one-hot encoding from previous. We're just going to be looking for we're just going to be generating a word, right? A valid word. So on the input layer, we input 2 valid words. These are valid words in one-hot encoded style, embedded with a one-hot encoding. That's the terminology. And then we're going to output 1 word embedded with an one-hot encoding, and that's how we know it's SAT. Right? We are able to have a mapping between words and one-hot encodings, and we can go back and forth. And here we have 2 one-hot encodings coming in. Inference, magic weights. Remember, magic weights that were trained to get this right, right? These magic weights are trained to get this right. And then we produce one hot encoding out. That's it. Now, we've solved the massive problem. The massive problem is now we can have some way to represent words such that we can put them into a neural network model and have goodness. Good. All right. Solved. So now we can do everything else that took us to LLMs. Any questions? Pretty clear? Give me a thumbs up in the you know, in the Zoom, if you got it. Ooh, I went forward a slide. Hold on. Okay. All right, good. We got some thumbs up. We got some thumbs up. Thank you guys. Thank you guys. Good. This is the way in a classroom, I can see faces. Do you know how tricky it is to give a lecture without seeing faces? It's like, I feel like I'm talking to myself. Anyway, so giving me feedback helps me do better. I will do a better job at this with any indication of feedback. Trues in the chat, like, or wait, that was confusing in the chat. That all helps me do a better job for you guys, so I can tell you exactly the magic key of information that can unlock understanding on your end, right? So feel free to engage however you can and give me hints. Okay. All right. So yeah, clearly one-hot encoding has drawbacks, like obviously, right? Like this doesn't seem that efficient. Ironically, this is exactly what Word Effect did. This is what the CBOW did. This is actually what happens, before we had smarter embeddings. Like that paper we talked about last time that unlocked deep AGI as we know it, used this. Like this was what they used. But then they were like, this is clearly not great. Here's why it's not great. So one is the width of the input vector scales with the size of the vocabulary. Ew, dude, like 500,000 dimensional vectors because you have to have a one-hot encoding for each word. Not great. The size of the size of your vectors, the size of the information you need to represent increases with the number of words. Not great, not great. And it's because you're using integers, right? And it's very crude methodology. Cannot scale to larger infinite vocabularies. You could take advantage of Zipf's law to get some optimization. So this is the law which one was this? This is the law that says the more common words in the language is used like exponentially more than the less common words in the language, and it's proportional to the rank of how common the word is, right? It just means that common words are used all the time over and over and over. And this gets to a hint to my question. Common words are used over and over and over. And you can take advantage of that, but you still have this issue, right? They can't scale to larger infinite vocabulary. So they have optimizations that take advantage of this. So you just use a subset of word and put unknown for certain words that are not common. One way you could determine if a word should be represented or not is you don't go to the dictionary for the English language, you go to your training set, right? So the dictionary might have 500,000 words, but your training set, what you're training on might only have 30,000 unique words. So then you just have to represent 30,000 unique words because there's no reason to have capacity for words that you're not even going to see when you're trained, right? So that was the answer to the question I posed earlier. Well, how do you handle unseen words? Well, you could have a special one-hot encoding for unknown words. Obvious drawbacks, right? Like, there might be something better, like if I saw the word jump in my data set, but I did not see the word jumped, ed with an ed on end, then should I just be like, I unknown, I don't know what that word is, so I can't even reason as an AI model. No, like that's not ideal. So that's another issue with one-hot encoding that was subsequently solved. Now, the biggest issue, and this is the issue that got us to accidentally realize, remember that accidental discovery I talked about last time? We accidentally kind of tripped into the idea that models can learn about the world in general when given a simple task, like predict the missing word, like OMG, right? Related to that accident, one of the things that drove us to that accident is trying to do better with this problem. With a one-hot encoding, the distance between each point in that vector space is always 1, right? Anyone that did a little bit of analytic geometry or anything, or even trigonometry and so forth, would understand what I'm saying. Cartesian coordinates, like one-hot encoding, the distance between any two of those points is 1. So the difference between cat and refrigerator is the same as cat and cats. That means that when the model sees cat and it sees cats, it's like those words are as different from an encoding level as cat and refrigerator. I can't tell the difference. If it sees mom and mother, or dad and father, it's like, I don't know that those are the same. Those are as different as mom and beetle, or dad and Sri Lanka itself, right? Like, so yeah, that's another issue. The distance between the words are always equal. Spoon and knife is as different as spoon and dog. And solving this problem in the representation space is how we got to that happy accident, that the model learns conceptual things well beyond what we trained it to, which we talked about last time. So in the ideal world, you want relationships with vectors between words. You want relationships between word vectors to reflect relationship between words. Features of word embeddings reflect features of the words. Okay. All right. Cool. We want something like this, right? We want your encodings to not have to be as big as the vector space, as the vocabulary space. So we like arbitrary length vectors to represent words because we can take advantage of real numbers. I mean, this kind of is a throwback to what we talked about before, right? We talked about how you use numbers between 0 and 1, right? Like we could do that here, numbers between 0 and 1. Well, that gives us a real space. This gives us a very rich infinity space with any number of dimensions, right? The could be 0.5, 0.8. Cat could be 0.10, 0.1, 0.4. So you have this infinity space now that you can take advantage of to be able to compress your representations. We want that. And we want apple and orange to be closer in distance than apple and drink, right? So you have drink here, you have drink juice. Those should be close. The representations should be close for juice and drink. But drink and rice probably shouldn't be close, right? So drink to rice is not great. You can't drink rice. I mean, in China, there's a very popular drink called rice wine that you can drink. So maybe it is a stronger connection. But in general, in the language, you can't drink rice, right? So you want those to be farther apart. Okay, cool. And so that's how we ended up getting this. Like I'm using this example a lot. I'm using it in many different ways. One, to show you what a feed-forward neural network is, and it's so simple and elegant, and it's how we accidentally discovered AGI was possible. Models can learn well beyond their thing. But in the pursuit of getting a better representation, that's how we got to the first. And this is how we get that better representation. We train the words on to be able to predict the word in the middle with Wikipedia. And then we can use this projection layer on the word to get numbers. And it turns out that the likeliness for the word to be here given this word, you can capture similarities, right? So cat and dog, you know, or let's say sat and lie, right? To sit or to lie, is going to be closer here because the cat sat on the floor, the cat laid on the floor is more similar. So this projection layer representation of these words will capture those similarities. That's why this was invented. And then we had our happy accident. Oh, crap. Oh, I don't have it here. But king minus man plus woman equals queen is like, what? The paper said that we were surprised that that was a thing. That means by getting better encodings, we're just trying to get better encodings so we don't have to have 500,000 dimensional vectors. By getting better encodings, we're like, oops, this model's learning about the world. What else can happen, right? Okay, good. We're here. Now you're an expert that got us to that one moment. What is a neural network? How do we represent words so that neural networks can see them and learn stuff about them? And then what got us to the AGI insight? I'm going to start calling it that. That's much more catchy than saying, you know, the self-supervised pre-training neural network insight, right? The AGI insight, right? All right, cool. Word to vec. Big paper. Change the field. Okay. And really, this is the summary, right? Traditional method was bag of words model. One-hot encoding is bag of words. Well, we'll talk more about bag of words. Just hold that thought. Each word in the vocabulary is represented by one position in a huge vector, EU. Blah, we know this. This is just summary side. Context information is not utilized. Not great. And then word embeddings gives us all this goodness, you know? Hello might be represented as that, unsupervised. Built by just reading huge corpus, stores each word as a point in space, latent space. OMG, the latent space insight. The development of human understanding around latent spaces is what's giving us the ability to generate images from words. It's wild. I have lectures on it. If you guys want me to talk about stable diffusion and these image generation, video generation models, and it's the same insight, guys, of this stuff that's relevant there. This one insight, understanding of capturing information in the latent space, that insight and that work is what is producing all of the AI understanding we have today. And indeed, there's a guy named Yann LeCun, beast. This is part of your education. So let me just show you who Yann LeCun is. Yeah, Yann LeCun. I spelled it wrong, but this dude. Yann LeCun. This dude, he was on, dude, watch this. Go to YouTube and watch this interview now, right? Because after the chat GPT, OMG, like this is so amazing. The world is different. Of course, the world is like, okay, like who are the minds behind this? Like where is our Einstein? And they're searching for the Einstein. And it's a battle. It's like Max Planck versus Einstein. If you know anything about physics history, there's Max Planck, there's Einstein, there's Einstein's wife. Who was the brains behind the operation? Somebody's going to take the credit. This guy's probably going to take the credit, dude. This is going to be our Einstein of AI, probably. But there's another good contender. I'll show you who it is. Let me just get another Chrome. This is interesting. Let's see. Let's get the pointer back. I'll do Jeffrey Hinton. Oh, the drama is so rich. The drama's so rich. Jeffrey Hinton, another one. Oh, it's a battle. And actually, I'm going to give you a fun way to think about this that could be somewhat inaccurate with around the edges. After ChatGPT came out, you remember Google went nuts. Oh, we invented the transformer, dude. Not AI. We invented all this stuff, and they're getting all this love. Jeffrey Hinton's part of the team that was doing this work at Google. He's on a lot of papers I'm pointing to, right? And he also won a Turing Award. This guy also won a Turing Award, Yann LeCun. They both won a Turing Award at the same time. You want to know why? Turing Award is like the Nobel Peace Prize. No, the Nobel Prize of Computer Science. They both won it. You want to know why? It's unclear who the Einstein's gonna be. So, but this I don't know. Like Hinton recently left Google. I think he's like, the anecdote is like he's in a retirement mode. He's like, screw this. He got really mad, dude. You should watch some interviews of Hinton post ChatGPT. Dude's bitter. And I love the guy. Actually, I met him at Google when I was interning a long time ago, and he was there doing the preamble to this work. He's a great guy. He's huge. I love how he talks. He always uses his hands. He's like models this and that. I love him. But he got really, you could tell he's a little bitter, and then he like quits, and he's like, this is all bad, not good. And then Yann LeCun's like doing Lex Friedman and stuff. Hinton might have done Lex Friedman. Watch this. Anyway, I'm gonna pop the stack. I'm gonna pop the stack and link it. Yann LeCun's obsessed, and he talks about this in this Lex Friedman. You should watch this Lex Friedman interview of him. He's obsessed with embeddings, latent space, the thing that produces stable diffusion, that way of doing AI. Because, and I'm gonna tell this for the nerds in the room, because what we're currently doing with GPT, ChatGPT, the generative pre-trained transformer, using the decoder to predict the next word based on the last word, predict the next word based on the last word, predict the next word based on the last word, is a slight divergence from the embedded space juiciness that was running the show right before ChatGPT was launched. ChatGPT and GPT-4, GPT-3 got popular because it was able to do some interesting things, but the core theoretical foundation of it is a little bit of an engineering hack on the principles of capturing knowledge in a latent space, embeddings, representations, snapshots of neurons firing. I can talk more about this all day long, but I'll never get through these slides. I hope you ask me questions that get me to talk about it more. Okay, let's move on. So big realization. Latent space means a multidimensional Cartesian space, and the points in that space representing meaning in some way. You can think of it like that. And that's actually, insights around there is how you can get a picture of a human that doesn't exist, right? It's because of that, the richness of the points in that latent space, that compressed space. It's very, very mind-bogglingly juicy. But we'll talk about, if I do the stable LM, I'll be able to spend a stable diffusion lecture. I'll be able to spend more time on that. Okay. Now, okay, so we did that. Okay, there's some problems. And you'll get this trend in this talk, right? Can we do better? This keeps coming up. Like, this is what we do as scientists. And actually, Yann LeCun's new theory is really what we need to be working on is generations in the latent space. We shouldn't be predicting the next word from the previous word. We should only be thinking inside the latent space and updating weights while we're thinking. That's how reasoning should happen. It shouldn't be generate a paragraph, model reads the paragraph, generates another paragraph, model reads the paragraph. That's how reasoning's happening today. Anyway, so that's actually interesting. But that's another question of, can we do better? Can we do better of all this GPT stuff? Yann LeCun's working on it. Let's wait. I think it's going to come. I think it's going to be interesting. I think he's on to something from what I understand him doing. Okay. There's actually a problem. There's actually a problem with that approach. Let me be more specific. Let's see, wait. Let's find a good picture of it. This thing's not great. This thing produced this and this insight, but there's a problem with it, okay? So let's see what the problem is. What's the problem? The problem is this, it's a feed-forward neural network. It's continuous bag of words, guys. All right, I'll tell you specifically, and then I'll tell you intuitively on the next slide. Okay, so specifically, the order of these input words, remember they're words, one hot encoded word. Each input is a one hot encoded word. The order, the model can't tell because of this sum at every node, there's a sum in a feed forward. So it doesn't see the order, right? That's a problem because this squishes the ordering. All right, let's talk about it intuitively. It's a problem. And you know how we get on these problems in AI? Like in AI, you're like, the problem comes from the gut. I built a neural architecture, and the way the data hits the model, just the way it hits the model, I think we're losing some information. It's information theoretic. Actually, information theory and deep learning is like married, right? It all comes together, which is beautiful. Like physics, entropy to information theory, deep learning, which is information is lack of entropy and order, patterns in space. Then comes to deep learning, right? Like it's wild. So you could say, we're losing information in this neural network architecture, gut. What if we try to capture, what if the weights could capture that information somehow? If we force magically these weights to be the right value, what the values of the weights are should be affected by the order of words. How do we solve that? Okay, this is the problem intuitively described, okay? There's actually a problem. The man blanked the dog. The model sees that as the dog blanked the man. It can't tell. It's a jumbled up set of words. It's a bag of words that the model sees to make that prediction of the missing word. So it's really just looking at a cluster of words, and it says, if you had to add a word to that cluster, what should it be? Right? This continuous bag of words is like, give me a cluster, add a word to the cluster. What should it be? The model says pets, right? The model might say bites. But the order matters. The information and the ordering of the words. The man blanked the dog should be the man pets the dog. That's more likely than the man bites the dog, because men don't bite dogs. I mean, most don't. I can't speak for every man. And then the dog blanks the man. The dog is most likely biting the man. It's not going to pet the man, right? That information is lost in that prior model. Even though it was able to do man minus woman equals queen and it was that smart, we're losing that information. So what happened next? Well, the problem is this basic neuron. Ew. Can't see, you can't see the order. You just see the values because they're squished and summed, and then you have an activation out of like, beep. I'm just seeing a bag of words. I'm not seeing the order. Okay. Well, brilliant scientists, and this is going to get a little confusing for probably some fraction of folks, but it's okay. Ask me questions, and I'm happy to clarify. If you took this model and you turned it on its head, they're like, all right, well, and then you were to split this up into three separate inferences. It's actually the same weights because the weights are hidden. But if you were to do this as seven separate instances and then be able to reroute the prior inference into the next inference, and then reroute the prior inference into the next inference, the order will matter. Let's look at it a different way. So just for reference, just look at that, because I'm going to show you what an RNN looks like. This is a recurrent neural network. We'll talk about it. In contrast to a regular NN, right? So this little highlighted area of this model is represented by this. This is essentially that redrawn as one little path, and just use it for reference. We're going to look at a recurrent neural network. So we talk about deep neural networks. This is a basic deep neural network thing, neuron organization. Now we're going to talk about a recurrent neural network. Okay, what's a recurrent neural network, everybody? Well, let's see. If you looked at this little sliver, that is represented by this thing, right? That thing is that sliver, okay? And there's something new on the input. Can anyone say in the chat what's new in the input? Just drop it in the chat. On the input, there's something added over on this side, on the right side here. What could it be? What's new on the input? Exactly. So I got a direct message from, well, it's a direct message, I won't say their name, but from a studious student, insightfully proposing that this is new on the input. Absolutely correct. So what is this thing? Well, in the context of the first X1, it's nothing. But the neural network architecture can accept H's, not just X. X corresponds to the word. H corresponds to the hidden layer. Well, the next one will correspond to Y, but this is the hidden layer. So this is blank on X, the first word, because there's no previous. Let's go. Let's understand this. So X2 has H1. Interesting. X3 has H2. These H's come from the previous X. So X's2's H goes into the next inference. So this is no longer one inference, it's three inferences to train. And you're training the weights with information about not just what the X is, but also what came before it. What was the hidden representation? And you can think about that as the embedding of the previous word. So it has two pieces of information and it's sequentialized. It's recurrent. What does that mean? If man is over here, that's going to give you a different H1 than if dog is over here. So all of a sudden, when you're training this model, every word can see the words before it. They can see the activation or the activation output, the hidden representation of the word before it, along with its current word. Recurrent neural networks. So somebody was like, all right, cool. You use a feed-forward neural network bag of words thing where it doesn't matter what order the words are in. This should be able to capture more information because it'll be able to see the words before it. And this is the same weights over time. So don't worry about that. This means the input now has information about both the word and the hidden words before it, right? And you're updating the same weights now with more information, with the contextual information around the word. Contextual. We're going to bring that back. Okay. That's a recurrent neural network. You guys are becoming experts, man. Like you guys are becoming epic experts. The math is actually very simple, right? But it's okay. You can just Google the math later. It means that for my hidden representation for some t, it's going to be a function of the weights of the hidden before and the word of t. So it's going to be a function of the weights with my previous h with my current t. That's all this says. It's easy, right? But yeah, you just read it offline. Understanding it is more important. This is just for documentation. Okay. Now, okay, there's problems. There's a better way to do this. I'm going to do a quick aside. I have a lot of slides on this, but there's a particular kind of recurrent neural network that we like to use and that the community was gaga about. For like 2 years, there was only papers. Pre-transformer, before Google invented the transformer, for like 2 years, everybody in science was working on this thing. It's called the LSTM. So why do we have LSTMs? LSTMs is a type of RNN. So there's a pure unfolded RNN. That's what I'm showing here. There's another thing called the LSTM, and then there's something called a GRU, gated recurrent unit. Dude, Google those things and you'll become experts. But I'm going to show you the popular one. The problem is vanishing exploding gradient problem. That is, if you have too long of if you have too many words, right? Of course, some information from H1 is going to propagate to H3, but the length of that propagation, at some point, H1 is going to disappear. It's going to get squished away, so that word number 74 isn't going to be impacted by word number 1. But if word number 1 was like winner, and then word number 74 was like loggy, and it was like winner of the illustrious prize that means that you're the best person on the human planet, and there's always a bunch of winners, blah, 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 is loggy, right? Knowing that the winner is loggy, you will lose that if there's too many words in the middle. That's the vanishing gradient problem. All right. So I'll leave it at that. For the folks that want to dig deeper, I'll let you dig deeper, but let's look at an LSTM. This is another picture of the vanishing gradient problem. It means that hidden layer, let me go back. Hidden layer number blah, blah, blah. If this is sufficiently large, hidden layer over here is not going to really remember this value won't, okay, why is this keeps turning off? This value, which ultimately impacted this value, which will appear to affect this value, right? Like this will get smaller and smaller as this becomes wider and wider, right? So that's a vanishing gradient problem. How do we solve that? Long short-term memories or gated recurrent units. The beautiful thing about this, and the reason I want to talk about it, is this is actually what disrupted the whole world as the next disruption after word to vec, which was the king minus man equals queen. The next version of that was an LSTM-based approach called ELMO. So it's important to know it for that. And also, I want you to get an understanding of the art and magic and craziness of what neural network architectures are and how people come up with shit, that works by engineering it. It's alchemy on the model. A neuron, right? Which is firing, which is activations. It's wild. Watch this lecture again, and if every time you watch it, read a paper, watch it, you'll understand what I mean. So what is a LSTM? Okay, this is the same thing, drawn a little differently. X, we've got our H's. This H actually goes in, right? This H actually goes into the next one. It's not fully represented properly, so this is the same thing, but look at what's in here. Inside of this thing is a machine. This is a recurrent neural network, same stuff, but there's a machine in here. And then there's this thing called the cell state that goes through this machine. It's wild, and it's just weights. It's just weights. I'm not going to get into all the details, but read up on it, but I'll give you an insight as to what this guts are doing inside of each cell of the neural of LSTM. So you have a cell state. This is almost like it's a value that represents remembering, right? And it's going to pick up things as it goes through to remember more or remember less. It's wild. Okay, so this is our remembering constant that goes through this thing, right? Okay, all right, let's just leave it at that. Okay. And I'm just going to try to make this intuitive without getting into too many details. Oh, wait, actually, there's a good slide here. And these guts are organized to have a sub-machine, and I'm just making this understandable. It has a subcomponent for forgetting, for amplifying, and for forgetting, for figuring out how much it should pay attention to current. So how much should I forget the past? How much should I pay attention to what I'm looking at? And how much should I amplify the output, for the future observations? That's what the guts here do, right? The magic of it is just, it's doing that out of weights. This will come back again when I talk about transformers, attention mechanisms. And I know I'm going to lose. Look, it's okay if you get a little lost on this. You can dig in more, but try to capture the intuition, right? So the machine is, we got to forget. So this is essentially going to squash the value. Remember, just imagine your cell states are values between 0 and 1. And you're just you're manipulating how strongly should I capture what's going on right now and take that into the future, right? So here we squash it for forgetting, right? So we use a sigmoid. There's details, number between 0 and 1. You multiply it, so you squash it. So this is the forgetting part of the machine. Weights to determine how much to shrink this value, the cell state. There's also something like a tan. You don't always have to use sigmoids. Sigmoids gives you values between 0 and 1. Great for forgetting, great for squashing. When it's like you're trying to add or subtract, like tangents are good for that as an activation function. So you'll get a number between -1 and 1, right? So you can use it to like add or subtract, right? Like, let me shrink or implode, or, how much should I pay attention to what's going on in this X1? That's what this part of the machinery is doing. So we forgot, ignore the past, go. Okay, how much should I pay attention? Go, right? And these are just weights. These are just math. It's just values that are learned, right? And then how much should I amplify the hidden output that's going out, right? And so this is the third part of the machine. So inside of each one of these cells, you've got weights that are organized on the hunch of a machine. And it works pretty damn good. It works better. Instead of like 74 window, now you can do like 1,000 window. So this was insane, right? There's different, and you train it just like every neural network, etc. It trains just like any. It's a deep learning thing. It just has a lot more weights. It's not just one weight on one line. It's got all these complex weights to forget and remember and send values through. And it's just somebody's hypothesis around how information should be learnable. What is the architecture of information that should be learnable, right? Wild, magic, awesome. And and it solves a lot of problems. LSTMs was, dude, all the rage. Everybody was like, oh my God, LSTMs. You capture so much more information. The fact that you can capture sequence to sequence, the ordering of words or any information really allows you to learn so much more. Try reading a book by randomizing all the words of every sentence. A lot of us can't do it. A lot of us couldn't do it. So we lose a lot of information if you can't see the orders of words. Let's call it model dyslexia, right? And so if you can correct that with a sequence to sequence model, you can do a lot. So here's some applications of LSTMs that were popular. Image captioning. You have one image in, and then you let it write a sequence of words to describe it. Video activity recognition. So you have multiple frames of an image, but it's writing, it's doing a classification after it watches all of the video. So it's like cat jumping after it sees a cat jump over many frames. Video captioning is like, as the video is playing, we're going to do a caption of what's going on. Oh, it looks like the basketball player is about to dunk the ball. Oh, he just dunked it. And now he's starting to, he fouled somebody. And then parts of speech tagging, language modeling. This is like translation, right? So you're taking a sentence in one language and then you're generating a sentence in another language. Like LSTMs crush it for this. And then this took the crown, Elmo, right? Elmo. This is that paper. This is what beat word to vec. Everybody was a rage. Nobody was paying attention to this stuff. This was hot. This was hot in the scientific community. And this is essentially the ChatGPT research journey. It's just ChatGPT was like interesting and popular, right? This one's interesting too because it came from University of Washington. So it's a this one came from academia. Most of this stuff comes from Google or whatever, but this was an academic one. It took over. People were just using this for a while. But then can we do better? What happened next? Ooh, well, there's an issue with LSTMs, guys. There's an issue. The issue is, I might have to break this up into two lectures. So part 2 is going to come next time because I'm only on slide 37 of 79. So it's all good. It's all good. Part 2 is going to be juicy, but I don't even know when I'm going to stop. Like, I'll just let me go for like another 15. Maybe till the 30-minute mark. All right, we'll just go. But can we do better? Ooh, can we do better? Well, the problem with this LSTMs, the problem is that it's slow. It's just so slow, right? Here's why it's slow. You can't use GPUs because of the hidden layer. You have to do this inference. I'll just draw it. You have to do this inference. You have to do this inference before you can do this inference and train. And then you have to do this before you can do this because you have to get the H's as an input to the next one. So you can't parallelize that. I can't take a whole sentence and then just put it on a GPU and train the whole damn thing as a big go. But the results were insane. Indeed, it is quite possibly the case that this neural network architecture is fundamentally smarter than what we're using in GPT all day. I would argue that given how much better LSTMs was to word to vec by capturing sequence to sequence, that jump indicates that there's so much more richness when you fully capture sequence to sequence that it's probably better than the GPT approach, the transformer, the attention-based mechanism approach, right? Why do I say that? The transformer invention, attention is all we need, was invented to solve this problem. And the invention loses the sequence to sequence proper, but tries to capture some approximation of that called context. It loses sequence to sequence. It just has, what other words in this bag should I be paying attention to? That's it. It's an attention-based mechanism. So it's wild. Because this is so slow and that we can't use hardware, we can't use like fast, my mouse is tripping. We can't use like fast hardware to, all right, this is better. Because this is so slow and we can't use fast hardware because of this thing, we had to invent a model where we can do better than bag of words, not being able to tell, but try to capture some more rich information. And that information is just simply, what other words should I be paying attention to in this bag? That's what a transformer does. So the interesting point I'm trying to make here is this might be better. But because of the practical concern that you can't train this thing properly, right? You can't train it in parallel. You can't take all of the internet and run it through in an affordable way and in a reasonably bounded amount of time. We had to invent something stupider so we can put more CPUs on it. And that's how we got the attention mechanism. People are like, this is amazing, but it's so slow. We love the bag of words because you could train it in parallel. Well, what did we do? Well, we invented the attention mechanism. The attention mechanism. It's richer, but it's not sequence to sequence. It doesn't really look at order. It doesn't capture that rich information. But what it does look at is, given each word, how much should it pay attention to all of the other words? And there's a different value. And so there is there is kind of there is some order captured in a way, right? Because the amount that you, so this is the same. These are just, it's drawn as two layers, but this is just showing what attention does. Attention, the cat, blah, 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 the cat, blah, blah, blah. Attention says, my embeddings for cat, or my embeddings for each of these words should be relative to cat, and how much, the fact that I'm trying to capture cat, the representation for cat here should pay attention to all of the other words in the window, right? So that's the attention mechanism. So let's look at it a different way. So for every particular word in the sequence, right, you're going to have a vector of coefficients as to how much should the embedding of this word pay attention to the values of all the other words in the window. Let's look at it a different way. And this is why I have so many ways of looking at it, because I know it could be like, let's see. So pollution should pay attention to the other words was caused shipwreck, right? So these other words should impact the representation for pollution in this context, contextual embeddings, more so than by the. It should pay attention to these words more. And then shipwreck also should pay attention to these words more. So that's another way we capture attention. Here's another view of the same thing, trade. So this is kind of like our two layers I was talking about, right? So for each word, you'll have a different distribution on how it should pay attention to the other words. For instance, it should pay attention to animal. The animal didn't cross the street because it was too tired. It really should be paying attention to animal. That's the strongest link, right? Once the model is trained, you should have weights such that the it will pay attention to animal more in terms of the embeddings for it. That means if you for it, in the context of this sentence, it should be similar to the word embedding to animal in the context of this sentence. So it's contextual embeddings. It's not sequence to sequence. We're not sending any information word to word. We're just creating a representation for each word relative to the other words in the window of words it's looking at. That's why we have context windows, right? It's like, oh, well, you know, you want to use ChatGPT, you can only put 4,000 words in it at a time. That's your window of words. And all of the words are contextually encoded relevant to its neighbors. So the vector for this, whether it be 0.5 and 0.8 versus 0.10 and 0.1 and 0.01, will be relevant to what other words are in the window. And the attention mechanism is what's going to transmit the values from one word into the other. Very beautiful. And why did they do this? Because you can do it in parallel. Each one of these can be done independently. You can GPU this bad boy because you can train all of the words simultaneously by looking at all of the words simultaneously. That's why. Google invented this because Google likes parallelism, and they were like, LSTMs are too slow. Wild. Boom, huge paper, theoretical paper. Attention is all you need. Classic. This is going to win all of the awards in perpetuity. This is like, this might be like E equals MC squared, right? What's the nuclear reactor? Nuclear reactor is a transformer, right? So that's the theoretical, this box. Multi-head attention. Just this box is that paper. Of course, the paper was written with the transformers too, but there's two papers, right? There's a BERT paper that really shows the power of embeddings in practice. I'll call that the nuclear reactor paper. Attention, all you need is like the E equals MC squared paper, right? So we went from this, slow to train, maybe smarter, to this, fast to train, highly parallel, could win with big data and big compute. And that's the core of a GPT. But, ooh, I don't know. I do have some time. I have 15 minutes. I'm not going to go into all the details on this slide. I have a whole lecture that describes attention mechanisms, but it's so beautiful. Let me just say, this is actually what goes on in a transformer. These are weights. Like you'll see the formulas and you'll see Q and K and V and all this craziness. This is a beautiful picture because it shows you, given the words, you have representations for the Q values, which represents the queries. And then you've got representation for the key values. So it's kind of like a key value lookup. Dudes, this is what I'm talking about with the weird engineering weights alchemy. Someone was like, oh, well, let's treat it like a lookup and like, let's construct some weights that can kind of learn looking up stuff. So key value, query key value, etc. It's fuzzy AF, but it's inspired by engineering in weights. It's wild. And so what happens is every value will have these learned independently, and then they'll be combined to create this softmax. This is the embeddings. This is the softmax applied to the values of all the other words, right? These V's. This is the softmax applied to the value. So for each word, you'll be able to get a representation of the word that's based upon the values with an attention, proportional attention. You have these magic numbers, but then these are reduced. These are heuristics. You essentially get a softmax, which is a probability distribution that sums to 1, right? That to apply to all of the vectors, and then that'll impact your Z value here, right? So that's what this shows too. It's a very beautiful thing. I'm happy to go into more details and describe exactly what's going on here, but I mean, it's a wild invention. I mean, it's very creative and it works. And so that's what ran on the world. BERT, nobody heard about this stuff yet. There was no chat GPT yet, but it was invented. It was all there. OpenAI did the first GPT here. Nobody paid attention. BERT came out after OpenAI did the GPT work. And then that was BERT. I'm going to do a quick, let's call it a preview, because I'm going to start there. I'll have enough time to finish this and then talk about projects and stuff next time. But that was BERT. I'll give you a preview of what then happened. And then there was this weird idea. It's very interesting. This is where Zero Shot came from. It's BERT. It's the same people. These are the same authors of Attention is All You Need, BERT. This is Google. They came up with the whole GPT is generative AI, is AGI. This is really the AGI paper. People are going to look back. Nobody calls it that, but this is the AGI paper. This essentially said you can solve all kinds of tasks by only pre-training. Unifying the training and objective. Oh, there's a great title for the paper. Oh, here it is. Oh, exploring the limits of transfer learning with unified text-to-text transformer. This unified is what inspired Don't Fine-Tune. Very, very wild. So we'll talk about that. This is the T5. This is where Zero Shot really happened. And then OpenAI with their GPT, they're like, dude, let's win. We're a startup. Let's just make it really, 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 really big and then run it on our world. And then same thing. Of course, it happened with T5. But this is where the Zero Shot really was popularized. Zero Shot, one shot, few shot. It's already dead. This used to be all the rave before ChatGPT. Now it's already, this terminology isn't used so much. It's really ChatGPT or AGI is kind of used now, but pre-trained versus fine-tuned. And then that was this paper. This is the GPT-3 paper. That was our Zero Shot paper. Then you can see the scale of the models. We'll talk about this next time. And we'll talk about GPT-3's dominance, and then we're going to talk about ChatGPT. We're going to go deep on ChatGPT. Like what the hell? What did it do? What is this reinforcement learning? What? Oh, human feedback? RLHF? Reinforcement learning with human feedback? You'll understand all this stuff. That's why I said you're going to be an expert by the end of this. You're going to understand it at the same level of fidelity as to how that works. How did GPT work? What's the magic? SFT, that's supervised fine training, PPO, principal proximal optimization, PPO, PTX, customization on that. That's how we got all these wins. This is GPT-3. This is Chat GPT, actually, literally Chat GPT paper. And then that's this deck. So I'll stop. Where did I stop? I'll stop here. It was right before this. Yeah, Bert. Yeah, this one. So we talked really to attention. And with that, guys, questions. All right. Can we say the attention model is like a weighted bag of words with ordering? You could kind of say that. You can kind of say that. I mean, it's really I mean, attention was such a good name, right? Because it's very kind of aptly put. It's really, when I create the representation for this word or the embedding for this word, the activations for this word, what other words should I pay attention to? And it's not even the order isn't really captured. It's more like how strongly I should pay attention to that's captured, right? It's not even like it could have been before animal, the dot could have been before and then you would get the same embedding out of this thing, you know? So the order actually doesn't even matter. But you do get some information about ordering capacity in the model, given the sequence of unique values that you have here. So it's very fuzzy, but at its most rudimentary representation, if these weights, if you randomized the ordering of this and had the same relative values for each word, you get to the same embedding, same representation. So order doesn't even matter, right? It just learns how to pay attention. In that learning, it learns how to pay attention. So one would argue then that, okay, yeah, maybe the mechanism for inference order doesn't matter. But in order to learn that this is a connection, that's going to be from seeing so many examples of sentences that the weight that this then freezes to would have come from some notion of the ordering pattern across words, because you're snapshotting a context. So you're creating really a representation of a paragraph. And that unique representation that comes from the summation of representations with attention has learned something about the order of words. So I think that would be the most accurate thing. Yeah, very good. Any other questions? That was a good question. Any reference papers to get started on this journey, like intro into the AI world stuff you could recommend? Guys, that's such a good question. So let me answer it in a couple of ways, right? Part of the answer to that is relative to what you want to do. Because if you want to build cool stuff, that's one journey. These lectures will be all you need if you want to build cool stuff, to dig into the models under the hood, right? Because wielding the models is an art form in and of itself that I haven't even talked about yet. We're going to talk about that. Like, how do you get these models to solve your problem? Custom. Like, we haven't even talked about that. What's prompt engineering? What's prompt training? What's LangChain? What's DSPY? What's neurosymbolic programming? Like, that's all coming. Like, how we actually use these machines, the nuclear reactor engineering stuff, we haven't even touched on. Right now, we're really talking about E equals MC squared. So that would be a place to start. And I'll create a list of links, honestly, for each one of these journeys. So if you want to build cool stuff, that's a journey. If you want to understand the E equals MC squared, that's a good journey too. And this talk is a roadmap of papers that would get you pretty primed. And then there's a whole bunch of offshoot papers you'd want to read if you want to get into the alchemy of model architectures. The problem with being an alchemist of model architectures is it's really expensive. If you create a new architecture and you want to test it and compare it to the previous architecture. You need GPUs, you need to train, it's crazy. So it's hard to be an alchemist without a good set of GPUs. Now, there's an asterisk there, right? Because there's an open question as to how you train small language models. What kind of alchemy can you do to a small representation? Then you can actually afford training it more. So there's a journey for that. And I could create a set of links that'll take you on that journey. But one thing that might be useful is to get the foundation of deep learning, do one of the lectures, do one of the courses online. There's a lot of really, really good professors, dude, that have taught this. Like Andrew Ng has one that people like. I don't really like it. I mean, no, I mean, let me not say I don't really like it, but I'm just saying the Andrew Ng one is, it's hard to see the link. See, one thing that I'm doing that you probably won't get to see much, and very few people do this, is they actually relate the theory. I'm trying to relate some of the core intuitions around the theory back to what you're seeing. When you take Andrew Ng's class, that link is a little weak. So you're just going to be looking at math formulas and you're going to be like, okay, I don't know why that matters. But like even the insight about sequence to sequence and how much more you learn there can be easily lost with one of the lectures you get online. So one thing you could do is use maybe these talks to be a map into what to dig deep on, and then read papers for the alchemy journey. So like that's another place you can start. I mean, I'll put together some links and share it in the Piazza for everybody. Loggy, remind me, pester me to make sure I do that if I forget. Any other questions? That was a good question. Yeah. Hit me up on Discord. I'll be there. Happy to connect and just point you in various directions. I also look forward to learning about your guys' background. Like, anyone who wants to come on and help with the Joseki mission, which is an open source research mission, and the incubation lab mission, which is the same mission, under the umbrella of a partnership between BCS and Joseki Labs, like, reach out to me. I'm happy to learn more about your backgrounds, what you're good at, and be able to maybe engage you on that journey. So feel free to reach out to me on Discord all day. Awesome. Any final? While developing a neural network model, how can we find the best, most optimized model? I mean, how can we get to know about the number of layers of neurons for the best model? Yeah, I mean, so one of the things that'll happen, that probably happened from this talk and from later talks, is an understanding of how to read the model descriptions and information. Almost every model that has come out has a paper. And we're going to be reading papers in this class, but every model has a paper. It's on archive. Every model has what they call a model card on Hugging Face. And you can read those to understand the parameters of the model. You'll observe patterns. You'll observe relationships, but being fluent and being able to read the model descriptions, this many parameters, that many weights. And I'll talk about this more next time. There's actually a really good slide for this, where I can describe what, like this slide, right? You've got how many parameters, how many weights, like you'll see things like that, how many layers. And so once you become fluent in understanding that, you'll be able to reason about it. But best model is that could be a trap, dude. It's because models, it's very, it's almost like there is no best. There's just these patterns, right? There's patterns like the more data, the better, the larger, the better. Reinforcement learning is really important for getting these models to do well. And then you can tinker with all kinds of stuff and then just get nice results. The thing you want to learn is how to prompt these models well and how to fine tune these models well. Just understanding the art form of that is probably a good way to spend your time, Awesome. All right. Well, I'll kick it back over to Loggy. Thank you guys so much. next lecture, we'll finish this and we'll talk about projects and like building cool stuff and like all that goodness.
Yeah, thank you so much, Jason. So that was amazing.
Anytime.
Yeah.
Yeah, man.
So I like the part of LSTM because many people in
Mm,
our department use LSTM for forecasting and prediction stuff. But the only issue
mhm,
is the delay, as you
mhm.
mentioned. It
Yeah.
goes for the forecasting delays. Yeah.
Exactly, exactly. I think that when it comes to time series, see, LSTMs is still very relevant. A lot of
Yeah.
folks will see the GPTs and get excited. Everything needs to be a transformer, but there's a place for LSTMs because they're small and you
Mm.
can pack a lot of intelligence in them. It's just really slow to train. Yeah,
Yeah. 100%. That's
yeah,
true. So
yeah.
yeah, I agree. Okay, Jason,
Awesome.
if you could share the slides with me, then I will
Yep.
upload to that place and I will share
Cool.
the Discord link with the others to connect to you.
Beautiful. Beautiful. Thank you all. Oh, today's Loggy's birthday, dude. Happy birthday, man.
Thank you. Thank you,
Dude.
Jason.
Awesome, man. Yeah, dude. Like, well, hey, yeah, well, be sure to, have a little celebration tonight. I know you
Yeah.
work so hard. I don't know if you're, I don't know if you're gonna actually like celebrate, but you should. Yeah.
Yeah. Yeah.
Mm, cool.
Okay, Jason. Thank you so much. So we'll meet
Awesome.
next week. Until then, thank
Yep.
you. Bye.
Yep. Thank you guys. Awesome. Talk soon. Yep. Later. Bye.